Welcome to this talk about high beam quality quantum cascade lasers for high power application from mirSense. This talk was possible thanks to many people in mirSense, in particular Grégory Maison, Michael Brun, Fahim Bouila, and Johanna Botre, and myself. We've been working a lot, especially during COVID, and here is the result of our work. First of all, I will present to you what is a quantum cascade laser and what it is for. Then, I will present to you the technology of quantum cascade lasers at mirSense. And finally, I will explain to you our circular beam technology and the roadmap for quantum cascade lasers at mirSense. First, I start with the quantum cascade laser technology. Quantum cascade lasers is an old idea that was proposed nearly 50 years ago. Indeed, as opposed to standard diode, there is no mean to have a good semiconductor-based mid-infrared and long-infrared emitter. Lead salts have been a possibility, but just only work at very low temperature. Thanks to the proposition of Karazianov and Suris in 1973, it was possible to think about a quantum well in which electrons transit from different eigenstates and release their energy through photons. And then they would cascade to the next level, as you can see here. It was only possible in 1994, thanks to the development of epitaxy, to create such a structure, as the layers inside the quantum cascade are as thin as 5 to 15 angstrom. And homogeneity is very important, and also the lack of roughness in order to have a high gain in the medium. And now that we are 20 years after the demonstration of these lasers, we are able to supply standard product, high quality, industrial grade. So it's been quite a journey. At mirSense, we have decided to exploit the QCL technology for two applications. First, in the defense, to provide high power, high quality sources for military application and defense application for DIRCM, for instance, as it is shown on this helicopter photo. But also, we can use the QCL to make gas sensors. And in mirSense, we just not provide the QCL, but we go up to the full gas sensor that you can see on the right. Of course, the topic of the talk is the market on the left, the defense market. mirSense is located in France, and we are vertically integrated. We have 3 sites in Paris, Grenoble, and Montpellier. The Paris site is responsible mainly for R&D for the lasers and also for chip production and test. The Grenoble site is in charge of packaging, beam aligning, and backend of the lasers. Where the site of Montpellier, which is a new site, is as well in charge of producing some other laser chips. All the production is done in France. So what can use the QCL for? Of course, in defense, the first application for which QCL have been developed since 20 years and successfully developed are the DIRCM, which means the ability to jam or a missile when it tries to target a plane or an helicopter. But we can use them for other purposes, such as illumination. We can use the fact that most military people have mid-IR receivers, cameras. We can use pointing in order to designate, for instance, something with our laser. We, of course, can use these lasers in labs to make lots of experiments that can be useful for defense. And for instance, also being able to use this experiment to test some equipments that work in the mid-IR. We can also use the QCL for CBRN detection, as you've seen that these lasers are able to discriminate molecules in a large amount of other interfering molecules. And finally, we can think of QCL as a good way of doing free space communication. And in particular, and we've shown it in you.mirSense, and together with Telecom, French University, we can use some chaotic encryption on the QCL in order to have high data rate with very low noise and very high security. What is an ideal QCL product? For the purpose we've seen on the last slide, we would say that a QCL should be able to emit at least 1 watt of mean power at the chip level. 10 watts would be ideal. It should be cost effective. If we think of semiconductor technologies, of course, we expect them to be reasonable cost, high quality, and compact. And it should be easy to integrate. When we talk about compactness, it's also have to be very reproducible. Power and divergence should be very close to one another for one laser to the other one, which means that you don't need to have all adaptive optics in order to cope with some change between lasers. We should have high beam quality. And this is something we can do with QCL. Unlike a lot of diodes, we can reach below 1.5 ohm square. And even if we could have a circular beam, that would be ideal. Of course, the laser is TM00, as it is emitting with an electric field perpendicular to the layer sequence in the laser. It's always TM, and 00 means that we are able to be spatially single mode. Then the power consumption is also very important. In this band, the wall plug efficiency of many sources is very low. And for QCL, we can expect, and we've been able to demonstrate, above 5 and maybe up to 10% of wall plug efficiency, which makes them among the best in this domain of all mid-IR sources. Also, we should be able to supply some driving electronics, as we know that these lasers require some specific voltage and current. And finally, that would be nice to be able to easily modulate these lasers and avoid any mechanical chopper or modulator in order to fulfill some complex scenario on the field. Let's have a look at the QCL at you.mirSense. So you.mirSense is 100% French-based. We are vertically integrated, as we said. We have a very strong relationship with our clients. We are very industrially oriented. What we aim at proposing is lasers always the same that people can rely on and build systems. And they could think, okay, QCL is a real product, is a major product, and not just a lab thing. So for that purpose, we are more than 20 employees now, and most of them have a PhD. And also we have semiconductor engineers and technicians in order to be able to assess production and test. We focus on strong partnerships with OEM contracts. And we have a continuous innovation process with main French institutes. And as you can see, the team likes lasers. So our QCL supply chain is very agile. As you can see here, a QCL is a very small piece of semiconductor, but for that you need clean rooms. And we have our own clean rooms in which we operate machine. We lend access to these clean rooms, and it's our own people doing the manufacturing. So we are not fabless. And for the limited amount of chips that are required for defense right now, which is below 1 kilo unit per year, it's absolutely sufficient. If by any means we would need to improve our manufacturing capacity, then we have already shown that our technology is easy to implement on a pure play foundry. But this is only necessary if we go to several kilo of units per year. And going above, then we would need maybe an even bigger factory. Above millions of units, silicon is the only way to manufacture such an amount of chips usually, and we've been demonstrating with the CA that we are able to do so. So our manufacturing process is totally agile and able to adapt to any kind of volume production, while keeping a very strong control either in France or in Europe on worldwide. Our supply chain is 100% European, from epitaxy to manufacturing in the clean rooms for the laser technology and to backend or assembly. down to the HHL package laser. One of the key features of mirSense technology is the dimensional controls of the manufacturing of the lasers down to 15 nanometers. Let me explain to you why this dimensional control translates into high reproducibility of the lasers and is a key for system development. On the right, you can see the reach of the lasers, and it is marked with two green lines, which are the size of the reach. If you change this line, you will change the mode size of the laser. If you change the mode size, you will change the far field. And if you change the far field, you have to change the system or to have adaptive optics to cope with the difference from laser to laser. And if you go down to 15 nanometers of control, then it's not a matter anymore. And you can have a system with no adjustable optics and change all the lasers without readjusting the system. So this is very important. If the manufacturing of the chip and the front end is key, it's not the end of the story. You need to have a proper back end, mounting, wiring, and then packaging of the laser. We've developed a capacity to handle chips from 1 mm to 10 mm in order to adapt to any power requirements at any wavelengths. On the left, you see our chips with the wire bonding. Then you see our HHL package and the board, the OEM electronics board, which control the laser, drive it, and also protect the laser by thermally regulating the laser and having all the securities. All these developments are worth it if they can pass through the qualification. Let me show you a film. This is indeed really shaky, and it shows you that we really shake the laser to be sure that when they are close to a turret, for instance, inside an aircraft, they will not be damaged and they will work properly. And in order to operate these lasers properly, we use quasi-continuous wave regime. This is a bit different than continuous wave regime. Indeed, in order to optimize the wall plug efficiency of the laser, we don't operate them at 100% duty cycle, but at 30 to 70% of duty cycle of a phase carrier modulation, which is basically a few hundred nanoseconds at more than 1 MHz. As you can see on the right of the picture, when we do that, there is a certain duty cycle for which the wall plug efficiency is still very high, since it tends to drop as the duty cycle increases. So there is an optimum, and this optimum is usually between 30 and 70% of duty cycle. If we are on the detector side of the system, for instance, being a missile seeker or a mid-air camera, at several megahertz, this is seen as a continuous wave, because the detector has a low bandwidth. And then on top of that, you can add a low frequency modulation, which is basically the system modulation that is required to perform the effect of the laser on the seeker, for instance, by lighting on and off at low frequency. This frequency can be typically few kilohertz. So here are the typical specs of our lasers. At 4 micron, below the CO2 atmosphere absorption, at 4.6 and 4.8, above the CO2 absorption, and at 9 micron, above the water absorption. The power we reach, diode level, or in the HHL package, are above 1 watt for most of the wavelengths, more than 500 milliwatt for the 9 micron, and we can reach 1.5, even 2 watts at 4.8 micron. Mode of operation is a Fabry laser in QCW, As explained in the previous slide, the advantage of QCW are to reduce the thermal dissipation by increasing the wall plug efficiency. And of course, all the costs that are driven by this thermal improvement. We use typically megahertz modulation for the quasi-CW frequency, and the pulse widths are of a few tenths of 100 of nanoseconds. Our electronics can go down to 20 nanoseconds. The beam quality is very good, TM00 and M² below 1.5. Laser is linearly polarized, and we provide a driving electronics as a PCB, or we can do custom solution on demand. Our strategy is OEM. We supply the laser as a chip, as you can see on the left, or inside HHL package, or with the electronics and the HHL package, and each of these components can enter a system. So our product lines is made of OEM solutions, I just mentioned, but also turnkey systems. If you want to test the technology, we can provide off-the-shelf turnkey systems that you can put in your lab. You just need a computer, the software we supply, and you can light on your laser. It's going to provide the optimum amount of power you require. For instance, we have 1 watt turnkey systems that are plug and play and just need a few minutes to be put in place and operated. We also do gas sensors. Just a word about our OEM module. It's a compact solution in which we stabilize the laser thermally thanks to the Peltier element inside the laser. And we also have a FPGA controller that enables embedded electronics and software such as onboard modulation, protection of the lasers, current, voltage, but also thermal protection of the lasers, can be controlled via USB using the computer or RS485 for an automat. The protocol is Modbus, and it works on the 24 volts standard supply, and is very compact and light. Here are some standard performance of lasers. As you can see at 4 micron, this is an example of random product 1 watt 4 micron lasers, random product 1 watt 4.6 micron lasers, and random product 1 watt 1.5 watt 4.8 laser. As you can see, the performance are reproducible for one to another laser at chip level or in HHL, and we are ready for mass production. This is the standard beam quality we get. As you can see, the beam is quite nice. It's quite Gaussian, as you can see on the right, with the Gaussian fit of the beams. Pointing accuracy of our assembly is 0.2 millifarad, and during operation there is a wonder about 0.2 millifarad when you change temperature, external temperature, power of the laser. If we are looking at the full module characteristics, you see that in order to extract 1 watt of optical power, you barely need to go above 20 watt if you operate below 30 degrees. Of course, if you are in the 30 to 40 degrees, you may have to increase the energy. So at the worst case, below 30 degrees, you are at 5% of overall wall plug efficiency, including the Peltier and the laser. And if you add the electronics, it's just a few watts of power more. So this is very efficient module. Some additional benefits of our solution: it's FPGA-based electronics, which means that we can embed complex modulation schemes or TTL. Also, we have the embedded stabilization and protection. There is a very easy to use software that you can see on the right for lab experiments or factory integration and settings of the system. And of course, Modbus for system integration is a standard protocol. Each of our lasers go through the burning process. We burn them usually at least 20 hours. Here you can see some laser operation during 20 hours. One of the lasers not passing the test. And if any of the lasers has a few % of change, it's considered as not compliant. The slight change you can see here is because during this burning, we add some low frequency modulation to stress the laser, to relieve the tension inside solderings and be sure that the lasers is going to live for a long time. All the other characteristics that we measure are the power, the consumption, and the beam quality. Now I'm going to talk to you about a brand new development that we've done in order to ease the life of our customers, which is the circular beam technology. And then I'm saying a word about our roadmap. So usually when you get an elliptical shaped laser, you don't want to play with that. And you usually have to use some complex optics to make it circular, which means that it's costly. There is a risk of degradation of the beam quality if one of these stuff is not properly glued or properly soldered, with the problems of vibration and military standards degradation. Also, if it's not properly done, and sometimes you cannot avoid it, you have a risk of astigmatism, as the laser is astigmatic after the first lens, because two axes don't have the same divergence. So, if you want to get rid of that, you wouldn't like a circular laser at cheap level. And this is what we've developed. Here on the left is a standard laser beam quality, quite Gaussian, but not circular. And on the right are examples of circular beam quality lasers that we've developed. The ellipticity is very close to 1. And the astigmatism is 0, which means that the beam is circular anytime. And right now, this technology is proprietary of you.mirSense and is available at 500 milliwatt power level and will be expanded to all product and all power by 2021. Here is another example of such unprecedented beam quality thanks to this circularization. You can see, you barely see the difference between the Gaussian fit and the measured beam on the right, and on the left, you see how circular and sharp is the beam quality. In the next 2 years, we plan to improve the power of our diodes, reaching more than 2 watts at 4 micron, more than 3 watts at 4.6, and above 1 watt at 9 micron. Of course, we continue to miniaturize our OEM solutions to increase the number of embedded functionalities. That would be as many functionalities that our clients will not have to implement, so it saves cost for everybody. And of course, we want to provide beam combined solutions to reach the 10 watts at the module level. This is just a picture to show you that these modules are ready for you. They are available, and here you see what you receive when you buy such an OEM module on the left in the case, and on the right you see 5 modules controlled with a single computer with a single Modbus interface. And if you look at this software, you see that we can control simultaneously as many lasers as we want, and we can change their mode of operation independently or together, and we can monitor their heat sinks independently as well. So this is very convenient to do higher powered solution by combining different lasers. Thank you for your time. I hope you enjoyed the presentation. I hope that you will like to use these lasers with these new features, easy to use with this circular beam that is really the first time that is demonstrated on QC lasers. So feel free to contact us, and of course we will keep you informed of our new development as they go out. Thank you very much for your time.